Welcome. Since you have arrived at this YouTube video, it is very likely that you are interested in hang gliding and in flight simulation, and most probably in the combination of those two. You came to the right place, although I have to tell you right away that the machine that I'm going to talk about does not exist, at least not as to my knowledge. Ever since I heard about the first virtual reality glasses, the Oculus Rift in 2013, the idea that it could be used to virtualize hang gliding very realistically has been playing on my mind. A while ago, I decided I should work out the idea in detail, and this video is the result of my work. I started out with modeling this hang glider and pilot in 3D software. Here in the lower left and right corners, I have several sliders. On the left are the sliders to control the pilot. They show the steering input that the pilot will give to make the glider go into a roll for a left or right turn, like this. Or to control the pitch and make the glider go faster or slower, like this. Notice that these sliders only control the pilot. While using these sliders on the left side, the glider remains in a neutral position and doesn't move at all. I can also make the pilot yaw, like this. This is, as you probably know, a commonly made mistake by beginner pilots when learning to steer the glider. These last three sliders here are to make the pilot look around in different directions, like this. This is just for animation purposes. The sliders on the right side only control the glider. I can, for instance, control the roll of the glider, like this. And I can also control the pitch, like this. And the yaw, like this. Notice that now the pilot remains in a neutral position. The sliders on the right side control only the glider, and the arms of the pilot just follow the position of the bottom bar. Last but not least, I can also control the bump, to make the glider bump up and down, like this. This sometimes happens in turbulent air. So I have a pilot and a glider in 3D that I can control completely. Now I need a 3D model of a motion simulator that can mimic the movements of the glider in the air. The best motion simulator for a flight simulation is a hexapod. Hexapods exist in reality in many variations and are used for all kinds of flight simulators, like here. I'm not aware of a hexapod for hang glider flight simulation, therefore I modeled my own hexapod in 3D, especially for this project. As you can see, when I use the sliders, the top plane of the hexapod aligns perfectly with the hang glider. And since the top plane of the hexapod is fully controlled by the pistons, we can now simulate all glider movements if we just attach the A-frame, the steering frame of the glider, to the top plane of the hexapod. Once we have done that, we can then just as well remove the hang glider, like this. We are now left with a motion simulator whose pistons can fully be controlled by sliders and therefore also by flight simulator software. Now the question is, how can we make this hexapod motion simulator, in combination with a VR headset, behave in such a way that a hang glider pilot can hardly distinguish between a simulated flight and a real flight? To answer this question, we first need to go into some detail on how a pilot handles a hang glider in the air. Most of you will be quite familiar with the handling of a hang glider, but since it gets more complicated once we get to the virtualization part, it's best to go step by step from start. Let me bring back the hang glider for now. A pilot steers the hang glider to the left or right by shifting his or her weight to the left or right. Here is a slowed down animation that shows how it works. The glider is at this moment flying in a straight line in the direction of the camera. The pilot is attached to the glider at this point, and the center of mass of both pilot and glider is somewhere about here. To make a left turn, the pilot uses the bottom bar to push his body with both his arms to the left side of the A-frame. In doing so, also moving the center of mass to the left. This causes the glider to bank to the left, which in turn causes the glider to go into a left turn. How this works aerodynamically is for this project not relevant. All that matters for us is what the pilot does and how the glider reacts. In reality, a pilot will always have to overcome some resistance when steering the glider. And to make the glider more responsive, he will first pull the bottom bar down a bit in order to pick up some speed and then shift his weight. This makes the glider react more efficient. But to keep everything as simple as possible, I will leave these kinds of details out for now and focus only on this basic movement. Once we have converted this to the virtual world, all other movements will follow automatically. Once the glider has gone into a turn, the pilot shifts his weight back to the center, the neutral position, to establish a stable turn. And as long as the pilot maintains himself in the neutral position, the glider will keep turning to the left. In other words, the glider will circle around. At this point, I want you to pay attention to three things: the angle between the A-frame and the horizon, the position of the pilot's head. His head is tilted with regards to his body in order to keep his eyes aligned with the horizon. And the arms of the pilot. They are at rest and not applying any force on the bottom bar. Let's have a look at the forces that the pilot is experiencing at this point. First of all, there is a gravitational pull. The gravitational pull is always pointing vertically down. Then, because the glider is circling, there is a centrifugal force on the pilot, working horizontally outside. The resultant is the force the pilot is actually experiencing. This is why the pilot does not need to apply any force with his arms to maintain his position. The resultant is exactly in a 90 degrees angle with the bottom bar. To go back to straight flight, the pilot needs to shift his weight to the right. For this movement, he will need to give a little more input, overcome a little more resistance than with the initial turn to the left, since he has to overcome more gravitational pull. After all, he has to push himself more up than with the initial turn to the left. How can all of this be translated to a virtual experience? We want to give the pilot in the flight simulator as much as we can the feelings he has in a real flight. But we cannot virtualize the centrifugal force, nor can we virtualize the resultant. What we can do, though, is we can manipulate the horizon, since it's a virtual horizon. When the pilot has his VR glasses on, he has no visual input from the outside world, only the visual input from the VR headset. And we can use this and gravitational pull to trick him into thinking he is in a turn and he is feeling the resultant force. I'm going to play the animation while looking at it with two cameras at the same time. The camera on the top, Cam 1, is a steady camera that films how a pilot handles a glider in a real flight. The camera on the bottom, Cam 2, is recording the exact same pilot actions, but the camera is animated to correct for the glider banking. The camera is counter-rotated in such a way that the glider remains more or less horizontal. Now remember that the difference in what you see is only in the cameras. Both cameras are filming the exact same pilot doing the exact same things. Keep in mind that Cam 1 is supposed to film the real-world situation, and Cam 2 is supposed to film a situation where the pilot is real, but he is hanging in a motion simulator and seeing the world through his VR headset. Remember the 3 points I mentioned earlier. The angle between the A-frame and the horizon. The position of the pilot's head. His head is tilted with regards to his body in order to keep his eyes aligned with the horizon. And the arms of the pilot. They are at rest and not applying any force on the bottom bar. If I undo the counter rotation of Cam 2, you can see that both Cam 2 and Cam 1 show the exact same image, like here. Now counter rotate Cam 2 again. Next, we need to look at what force the pilot is experiencing. As you remember in the real world, while in a turn, the pilot is experiencing the resultant of the gravitational pull and the centrifugal force. And it was this arrow. Now let's rotate Cam 1, the real flight situation, so that it matches Cam 2, the virtual flight situation. As you can see in Cam 1, the resultant is now pointing straight down. In Cam 2, the virtual flight situation, there is of course gravitational pull, but there can be no resultant, since we cannot simulate centrifugal force. But even though there is no resultant arrow in Cam 2, there is the arrow of gravitational pull. And since the pilot in Cam 2 has his VR helmet on, and the VR helmet presents to him a banked horizon, the pilot has nothing to distinguish between the force working on him in Cam 1, which is the resultant, and the force working on him in Cam 2, which is gravitational pull. To the pilot in the virtual flight situation, it is just as if he is banked and if he is circling. Let's take the next step and remove the glider. I'll leave the pilot just with his A-frame. Earlier, we went from Cam 1, the real-world situation, to Cam 2, the hypothetical virtualized situation. Now I will go from Cam 2 to Cam 3, where I convert the hypothetical virtualized situation to the real-world hexapod. I mentioned earlier that a pilot who steers to the left or to the right will have to overcome some resistance, especially when steering out of a turn. This initial resistance can very easily be simulated by the motion simulator. The simulation software gets steering input from the pilot. The software also controls the pistons. So when the software gets steering input, it can hold the pistons stiff for a short moment, giving the pilot the feeling of resistance, and then start to bank. Same when steering out of a turn. The software knows that the pilot is in a turn, and when noticing the pilot is steering out of the turn, it can hold the piston stiff for even a little bit longer. Since for steering out of a turn, the pilot needs to overcome more resistance than for steering into the turn, as you can see here in the animation. All these principles that work for roll will work for pitch also, and for any combination of roll and pitch. This of course provided that the movements are not too abrupt or violent. Steep turns and high-speed movements won't be realistic, but for a normal cross-country flight, the simulator will work. And not only can the motion simulator react accurately to steering inputs of the pilot, it can also react accurately to virtualized thermal activity, turbulence and other weather forces. Thermal activity, turbulence and other weather forces can be translated into piston movements, causing the A-frame to react. For instance, a pilot who flies into a thermal can be thrown out of the thermal, just like a real flight situation. And when the pilot successfully manages to circle inside the thermal, the simulation software will show him he is climbing. I think that a hexapod, together with a VR helmet and high-quality flight simulation software, can simulate a hang gliding flight in such a way that it is very hard for the pilot to tell the difference. If not now, certainly in the next 5 to 10 years. Flight simulator software and VR headsets become more realistic every year, and it offers more and more options with every update and upgrade.